Okay, hello, how are we? So, this is, we're doing Module 1 or Chapter 1 of the Cisco 3, which is Enterprise Networking, Security and Automation. And so the topic is Single Area OSPF version 2 concepts. So, of course, OSPF is an open source industry standard routing protocol that is very good for large networks. And yeah, is well supported and well thought of, basically. So what are we going to look at in this chapter? So we're going to look at the we're going to explain how single area OSPF operates in both point-to-point and broadcast multi-access networks. And so we're going to look at its features and characteristics, what packets it uses to exchange information, and how it operates in general. So how it makes its routing decisions and the like. Okay, so its features and characteristics. So OSPF is a link state routing protocol that was developed as an alternative for distance vector routing information protocol. And so RIP was the first routing protocol, at least widely used. And while simple to use, it does certainly have some limitations. And so OSPF is link state, which basically means it knows all the information before it makes routing decisions. While distance vector routing protocols, it's often called routing by rumor. And so basically, distance vector is basically all the routing protocol knows. It knows how far it is to a destination network, and it knows which link is the next hop, and that's all it knows. So that's why they sometimes call it routing by rumor. Okay, so OSPF is a link state routing protocol that uses the concept of areas. A network administrator can divide the routing domain into distinct areas that help control routing update traffics. And so that's why OSPF is so good in large networks, is you can sort of subdivide your network into smaller areas, and that actually decreases the amount of traffic that needs to move around, makes it a lot more reliable and a lot more scalable. And so hence the large networks. And so a link is an interface on a router, and a network segment that connects two routers, or a stub network such as an Ethernet LAN that is connected to a single router. The information about the state of a link is known as its link state. All link state information includes the network prefix length, and cost. This module covers basic single area OSPF implementations and configurations. Okay. So all routing protocols share similar components. They all use routing protocol messages to exchange route information. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets. And so there are hello packets, database description packets, link state requests, link state updates, and link state acknowledgement packets. We will go into their specific use in either this chapter or coming chapters. So these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the network. So the information that OSPF gathers, it actually organizes into a series of databases. And so the first database is the adjacency database. And so that is where the router keeps track of its neighbor routers. So it's a list of all neighbor routers which a router has established bidirectional communication. This table is unique for each router. It can be viewed by using the show IP OSPF neighbor command, and remember the American spelling. And so that will actually show you all the entries in that database. So there's a link state database, which basically, as it says, is the topology table. So that is all the information that OSPF holds about all the networks that it's been told about. And so it knows about every router that's in its area, and knows about every network that it's in that is in its area. And so basically, yeah, so all routers that are running OSPF within an area will have an identical link state database. So they all exchange the same information, and so they build the same database. And so if you do show IP OSPF database, you can actually see what is in that database. And so, and it is that information that is used to then create the forwarding database. And so the forwarding database is a list of routes generated when an algorithm is run on the link state database. Each router's routing table is unique and contains information on how and where to send packets to other routers. And so show IP route, of course, shows that. So basically, the link state database is the raw, all of the information, and then it actually uses the shortest path first algorithm, hence the SPF, or the Dijkstra algorithm, because he's the mathematician who invented it, is run on that database, and then that is what creates the entries in the forwarding database or routing table. And so, of course, each router will have its own unique routing table because every router is in a different part of the network. And so, all destination networks are in a slightly different position as compared to other routers. Okay, so we're still doing components. So the router builds the topology table using the results of calculations based on the Dijkstra shortest path first algorithm. The SPF algorithm is based on the cumulative cost to reach a destination. And so as a part of the process, the SPF algorithm creates a shortest path tree by placing each router at the root of the tree and calculating the shortest path to each node. The SPF tree is then used to calculate the best routes. OSPF places the best routes into the forwarding database, which is used to, of course, create the routing table. Okay, so how do these link state routing protocols operate? And so to maintain their routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. The following are the link state routing steps that are completed by a router. So establish neighbor adjacencies, and so that's using hello packets, and of course that is the adjacencies table, that we've spoken of earlier. They then exchange link state advertisements, and so basically they exchange what networking information they know, both of routers and links themselves. And of course, that's how they build up their link state database. Once they have got a complete database, they will then run the SPF algorithm, and that of course gets you the forwarding table, which of course is put in the routing table. Okay, now we did mention earlier that you can actually divide OSPF into multiple areas. And so, as I said, it makes it more scalable. So to make OSPF more efficient and scalable, OSPF supports hierarchical routing using areas. An OSPF area is a group of routers that share the same link state information in their link state databases. OSPF can be implemented in one or two ways as follows. So you can just do single area OSPF. And so, this would make it a small or medium-sized network. And all routers will actually know all information about all links in the entire network. And so typically, if you have a single area OSPF, you will always call that area area 0. With multi-area OSPF, it's implemented using multiple areas in a hierarchical fashion. All areas must connect to the backbone area. So area 0 is a specialist type of area. And so in a multi-area OSPF setup, area 0 would be in your backbone. All other areas would connect to area 0. And so routers interconnecting the areas are referred to as area border routers. And so basically, if you were to have more than one area, a router would actually have some interfaces defined as area 0 and other interfaces defined as area 1. And so that router, the area border router that I was talking about, would actually have two separate database sets, one for each area. So it actually has link state databases for both area 0 and area 1. And so that, and it's that area border router which will then control what information goes between areas. And so in this module, we're only talking about single area OSPF, so we don't have to worry too much about the complexities of multi-area OSPF at the moment. Okay, so the hierarchical topology design options for multi-area OSPF can offer the following advantages. So smaller routing tables. So here, as you can see here, this has actually got three areas: area 1, area 0, of course the backbone, and area 51, because hey geeks. And so basically, smaller routing tables are possible because there are fewer routing table entries. This is because network addresses can be summarized between areas. Route summarization is not enabled by default. So as you can see here, router 1 and router 2 are those area border routers we were talking about in the previous slide, because some interfaces in area 1, some interfaces in area 0. We'll have those two sets of databases, and one of the things you can do on an ABR is actually control summarization of routes. And so you can summarize all of area 1's routes and then advertise it in area 0, which of course then will go to area 51. And basically, that's all the routers from the other areas need, is a summary of that. And so again, as I said, it makes it more efficient. And so because of that, link state update overhead will reduce because there are less routers talking to one another all the time, and so it minimizes processing and memory requirements. And it will also reduce the frequency of the SPF calculations, so shortest path first. So OSPF localizes the impact of topology change within an area. For instance, it minimizes the routing update impact because an LSA flooding stops at the area boundary. And so basically, if you've got some unreliable routes in area 1, you will have a lot of link state advertisements floating around in area 1, but that will not move on to area 0 and area 51 because they only get summarized information of area 1. And so SPF, while a wonderful algorithm, is somewhat CPU intensive, and so you don't want to be running SPF calculations too often, just because the router might be so busy doing that it actually can't forward packets, and so that's not a good plan. Okay, now OSPF version 3 is basically identical to OSPF version 2, except it supports IPv6 addresses. And so OSPF version 3 exchanges routing information to populate the IPv6 routing table with remote prefixes. Note, with the OSPF version 3 address families feature, OSPFv3 includes support for both IPv4 and IPv6. OSPF address families is beyond the scope of this curriculum, so that's probably CCNP, you want to do that. Version 3 is the same functionality as version 2, but of course is designed for IPv6. And so, and of course, you need to be running version 3 on all the other routers as well. Version 3 also uses the SPF algorithm as the computation engine to determine the best paths throughout the routing domain. So OSPF version 3 would have a separate process. If you were running version 3 and version 2 on the same router, would actually be a separate processes. The processes and operations are basically the same as in IPv4, but of course separate or independent. Okay, so what packets do we send? And so the basic types of packets here that OSPF uses are types 1, 2, 3, 4, and 5. Of course, they do have names, and actually between version 2 and version 3, they are damn near identical. All right, so the first type of packet is hello packet, and it's used to discover neighbors and build adjacencies between them. And so that's how that adjacency database is built, by using hello packets. You receive a hello packet from a host, and of course you would send, you would also be sending them as well. Now, a database description packet is basically just sort of like a version number for the database. And so they will be distributed every now and then. And basically, hey, look, I've got version 53 of the database at the moment. What's everyone else got? And so as long as everyone else has got the same version number, we're all good, basically. That's in a very basic way of saying how it runs. Now, then actually actively finding routes. Of course, if a router needs to find a route, a link state request would be the packet that's sent, saying, hey, you request specific link state records from a router to yourself, of course, and the response to that would be a link state update packet. And so that's, of course, how those link state records are sent. That's not the only time link state update packets are sent. When a router forms adjacency will actually send an update unsolicited, basically, of, hey, these are the routes I know of. And so it will happen. Or when a router has a status change of one of its directly connected networks, it will actually send out a link state update packet unrequested as well. And so that will, of course, go to all its neighbors. And then there's the link state acknowledgement packet. And basically that is used to acknowledge all of them bar the hello packets, basically, just to make sure that, yeah, again, it's just informing the source that that packet has reached the destination. Okay, why isn't that going to the next slide? Now it's gone to 2 slides. Okay, link state updates. So there are actually different types of link state updates, or actually the link state update is the packet, and within it can be one or more link state advertisements. And then so those advertisements are about a particular network. And so, of course, you can include more than one in those packets. So LSUs are also used to forward OSPF routing updates. An LSU packet can contain 11 different types of link state advertisements. OSPFv2 renames several of these LSAs and also contains 2 additional types. LSU and LSA are often used interchangeably, but the correct hierarchy is the LSU is the packet, and within that packet you can have several LSA records or messages or whatever you, however you wish to say it. And so, as we said, the LSU was a type 4 packet, and then there are actually 11 types of LSAs within that LSU. And so you've got router LSAs, you can check for database synchronization, you've got summary LSAs, autonomous system external LSAs, multicast OSPF LSAs, defined for not so stubby areas, that's, yeah, non-standards based in anyway, and external attributes LSA for border gateway protocol, I'm assuming, not patrol. Okay, so let's have a look more specifically at a hello packet. So, of course, this is the entire packet here. So, of course, it's being sent over a link, and so it needs to have a data link layer header, and then, of course, the IP header, and then you've got the OSPF packet header. And so the header is this first part, and then the rest of the packet is the actual payload. And so OSPF type 1 packet is the hello packet. Hello packets are used to do the following: discover OSPF neighbors and establish neighbor adjacencies. Also used to advertise parameters in which 2 routers must agree to become neighbors, and can be used to elect designated and backup designated router on multi-access networks like Ethernet. Point-to-point links do not require DR or BDR. So basically in the header you would have the router ID. Now basically when OSPF starts up, it actually, first thing it does is actually tries to identify itself, so it gives itself a router ID. And so it's an IPv4 address. We will talk in more depth about that, but it will pick a number for itself as a router ID. As you can see, type 1 means it's a hello packet. And an area ID, remember we'll talk multiple areas. If we're talking about single area OSPF, that will be 0. And then so you can have checksums and authentication types and authentication fields in the header as well. So of course you can do the checksum, of course, is just to find errors. Authentication type, of course, says what type of authentication is going to be there. And so that's the header. And then the payload of the packet is there's the network mask, and then there's the hello interval. So how many seconds between hello packets are there? There's a router priority field, which can be used for that DR, BDR election. Then there's a DEN interval, which is sort of hello interval, of course, is how long between hello packets. dead interval is how long since I've gotten a hello packet will I declare that router dead. And then designator and backup designated router. And then a list of neighbors that it's already knows. And so that's the hello packets, and these are, at least some of these are the things that need to match. And so hello interval and dead interval must match. Area ID must match. Also the network and its mask must match. And so, and so they're the kinds of things that are used to determine whether you can form an adjacency. Okay, so how does it operate? And so basically, OSPF goes through several states. And so down state is, of course, it's not running, and it goes through several more states up until it's in the full state. But let's go back to that previous slide. So in the down state, no hello packets have been received, and so it will be deemed as being down. So no neighbors have spoken to it, and so it's in the down state. Now, the router you're sitting at will send hello packets, and so from there, once that has happened, it will then go into the init states. And so in the init state, initialization state, of course, hello packets are received from the router. They contain a router ID of the sending router, and then they can transition to two-way. Two-way just means that there has been communication in both directions. And so on multi-access links, the routers elect the DR and BDR in that state. And from there, they will then go to the X start state or exchange start. And so in the exchange start state, on point-to-point networks, there are two routers that decide which router will initiate the database description packet exchange and decide upon the initial DBD packet sequence number. Routers exchange DBD packets, and so after they've decided that, the exchange start state, then they go to the exchange state. And so that's when they exchange their database description, and then they will often send you link state updates and or requests in that process as well. Once that's happened, then you need to go to the loading state. And so also the LSRs and LSUs are done in that. Routes are processed using the SPF algorithm, and then you transition to the full state. And so the full state is basically everything is good. The link state database of the router is fully synchronized with its neighbors. And so they're all very, very happy and things are going well. And so when you do that show IP OSPF neighbors command, you would normally be looking for routers being in the full state with their neighbors, because that shows it's a happy place to be. Now, establishing neighbor adjacencies. To determine if there is an OSPF neighbor on the link, the router sends a hello packet that contains a router ID out of all OSPF enabled interfaces. The hello packet is sent to a reserved multicast address, which is 224005, which all OSPF routers will listen on. No other hosts will listen, just OSPF routers. Of course, only OSPF version 2 will process these packets because that's designed for IPv4. The OSPF router ID is used by the OSPF process to uniquely identify each router in the OSPF area. A router ID is a 32-bit number formatted like an IPv4 address and is assigned to uniquely identify a router amongst OSPF peers. When a neighboring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. And so, of course, basically, this is a blow-by-blow. The process routers used to establish adjacency in a multi-access network, so Ethernet network. So, of course, they start in the down state. When you enable OSPF version 2 on the interface, R1 transitions from down to init and starts sending hello packets out of the interfaces that are running OSPF. When a router receives a hello from an previously unknown router, it will add it to its neighbor list and responds with a hello packet containing its own router ID. So, of course, because if there's been communication in both directions, you're now in two-way state. R1 receives R2's hello and notices that the message contains R1 router ID and the list of R2's neighbors. R1 adds R2's router ID to the neighbor list and transitions to the two-way state. If R1 and R2 are connected on a point-to-point link, they then will transition to exchange start. If R1 and R2 are connected over a common Ethernet network, the DR-BDR election occurs. Now, of course, if there's more than one router on that interface, the DR-BDR election might have already happened, and yeah, we don't redo elections. And so the DR-BDR election occurs where the router with the highest router ID or the highest priority, that should actually be in the opposite order. Priority is checked first, and then the router ID is the tiebreaker. But anyway, and so the one with the highest router ID or priority is elected as the DR, and the second highest is the BDR, backup designated router. Now, the reason we do that is it just makes communication more efficient. Whenever, if you've got an Ethernet network in your core of your network, typically I'd assume, with lots of routers connected to it, instead of having full adjacency between that one router and every other router on that one, basically every router has full adjacency with the DR and the BDR, and they'd actually only stay at two-way state with all the other routers. And so then whenever there's a topology change, that router that discovers it will tell the DR, and then the DR will tell everyone else, instead of that router telling everyone, and everyone else will tell everyone else, and it just makes a lot of traffic. So that's why they do the DR and BDR. It just makes traffic a lot more efficient. After the two-way state, routers transition to database synchronization states. This is a three-step process as follows. They decide the first router, so who's going to start the database description process. They exchange them, and the other router must acknowledge each DBD with an LS acknowledgement packet, and then they send LSRs, requests, of course, to update their information. After all LSRs have been exchanged and satisfied, the routers are considered synchronized and in a full state. When a change is perceived, basically, they will send an LSU whenever there's a change in the network, or every 30 minutes. Okay, so, all right, going back to the DR process. And so this is the situation we're talking about. We've got one switch. All of these routers are hooked into it. 5 routers. And so with 5 routers, basically every router has 4 adjacencies. And so that's times by 5 means there's 20 adjacencies sort of being tracked by all the routers. And so without having a DR BDR, it just gets very, very busy. And so if this router senses a change in the network, it will advertise it to the other 4 routers. And of course, each router then will know that, hey, there's a change in the network. And so it will send it to all the routers other than the ones that it learnt it from, of course. And it just becomes a snowballing effect, even though those other routers already know, but they're just trying to be safe. And so that's the whole point of it. So multi-access networks can create 2 challenges for OSPF regarding the flooding of LSAs. You've got many adjacencies, so Ethernet networks could potentially interconnect many OSPF routers over a common link. Creating adjacencies with every router would lead to an excessive number of LSAs exchanged between routers, and extensive flooding of LSAs when there's been a change in the network, as I was explaining. And so LSA flooding with a DR, so an increase in the number of routers on a multi-access network also increases the number of LSAs exchanged between the routers. This flooding of LSAs significantly impacts the operation of OSPF. Every router on a multi-access network had to flood and acknowledge all received LSAs to all other routers on the same multi-access network. Network traffic would become quite chaotic. And so that is why on multi-access networks, OSPF elects a DR to be the collection and distribution points for all those LSAs sent and received. A BDR is also elected in case the DR fails, and so it can take over straight away. All routers that are not either DR or BDR are called DR other or druthers. A druther is a router that is neither a DR nor a BDR. And so the DR is the only is only used for the dissemination of LSAs. The router will still use the best next hop indicated in the routing table for forwarding normal packets. And so it's only about OSPF communication that the DR, BDR affects anything really. It just makes OSPF communication more efficient. Doesn't change anything else. All right, so we're pretty much at the end of the chapter now. And so what do we do in this? And so we spoke about OSPF, Open Shortest Path First. So it's a link state routing protocol that was developed as an alternative to RIP, because RIP had its flaws. Still does. OSPF is a link state routing protocol that uses the concept of areas for scalability. A link is an interface on a router. A link is also a network segment that connects two routers, or a stub network, such as an Ethernet LAN, that is connected to a single router. All link state information includes the network prefix, its length, and its cost. So cost is the metric that's used in OSPF. It's actually just calculated from bandwidth. So the higher the bandwidth, the lower the cost. Okay, so all routing protocols use routing protocol messages to exchange route information. The messages help build data structures, which are then processed using a routing algorithm. Routers running OSPF exchange messages to convey routing information using 5 types of packets. So there's hello packets, database description, link state requests, link state updates, and acknowledgements. OSPF messages are used to create and maintain the OSPF databases. The adjacency database creates the neighbor table, link state database creates the topology table, and the forwarding database creates the routing table. The router builds the topology table using results of calculations based on the Dijkstra SPF algorithm, and the SPF algorithm is based on the cumulative cost to reach a destination. In OSPF, the cost is used to determine the best path to the destination. As I said, it's metric. To maintain routing information, OSPF routers complete a generic link state routing process to reach a state of convergence. So they establish neighbor adjacencies. They exchange link state advertisements. They build the link state database. Once they've got a completed database, they execute the SPF algorithm. And from that's where they get the best routes to all the destination networks. With single area OSPF, any number can be used for the area. Best practice is to use 0 though. Single area OSPF is useful in smaller networks with fewer routers. With multi-area OSPF, one large routing domain can be divided into smaller areas to support hierarchical routing. Routing still occurs between the areas, inter-area routing, while many of the processor-intensive routing operations, such as recalculating the database, are kept within an area. OSPF version 2 is basically the same as OSPF version 3, but of course, version 2 uses IPv4, version 3 uses IPv6. And so, of course, they've just redesigned it to work with a IPv6. And so the OSPF uses the following link state packets to establish and maintain neighbor adjacencies and routing exchange updates. So hello packets, database description, link state requests, link state updates, and link state acknowledgements. LSUs are used to forward OSPF routing updates, such as link changes. Hello packets are used to discover OSPF neighbors and establish neighbor adjacencies, advertise parameters on which two routers must agree to become neighbors, and elect the designated router, and backup designated router on multi-access networks like Ethernet. Point-to-point links do not require DR or BDR because there's only ever 2 routers. Okay, I think we're nearly finished. Some important fields in the hello packet are the type, I think that's network type, router ID, area ID, network mask, hello interval, router priority, dead interval, DR and BDR, that's the router IDs for the DR and BDR, and the list of its neighbors. The states of the OSPF progresses through to do reach. The states that OSPF progresses through to reach convergence are down state, init state, two-way state, exchange start state, exchange state, loading state, and full state. Might have to edit that file. When OSPF is enabled on an interface, the router must determine if there is another OSPF neighbor on the link by sending a hello packet that contains its router ID out all OSPF enabled interfaces. The hello packet is sent to the reserved all OSPF routers multicast address of 224.0.0.5. Only OSPFv2 routers will process these packets. When a neighbouring OSPF-enabled router receives a hello packet with a router ID that is not within its neighbour list, the receiving router attempts to establish an adjacency with that initiating router. After a two-way state, routers transition to database synchronization states, which is a three-step process. Multi-access networks can create two challenges for OSPF regarding the flooding of LSAs and creation of multiple adjacencies and extensive flooding of LSAs. And so a dramatic increase in the number of routers also dramatically increases in the number of LSAs exchanged between the routers. This flooding of LSAs significantly impacts the operation of OSPF. If every router in the multi-access network had to flood and acknowledge all received LSAs to all other routers on that same multi-access network, the traffic would become quite chaotic and quite a lot. This is why DR and BDR election is necessary. So on multi-access networks, OSPF elects a DR to be collection and distribution point for LSAs sent and received. The BDR is also elected in the case the DR fails. I think that is now it. There's the logo. So that's Chapter 1 survived. Have a nice day, and I'll see you again for Chapter 2.